what you intend to do. Yeah. Okay, so okay, descriptive statistics, numerical and categorical. Okay, I think I've done. Okay, let's just run that before the t-test and one over and so on. ANOVA contingency. Okay, so let's go back. So let's go back to SPSS. Right. So for you to, or this is where you find your analysis. All analysis you need to do with SPSS. This is where you find it. From analysis, you go to descriptive statistics. So descriptives, you find frequencies if you're looking at categorical variables, or descriptives if you're looking at considering continuous variables, right? However, you can still do run continuous variables here. By the time, for example, you can add, say, height, okay, current age. So you go to statistics, you find whole lots of analysis that you want to run with that. You can find your mean, median, mode, sum, all that, standard deviations, minimum, maximum. You find all this you want. So pick whatever you want. As soon as you're done, click OK. Charts, if you want any charts, bar chart, histograms, like what I mentioned about looking at normal distributions, just the quickest way of charting, assessing if any data or variable is normally distributed is, looking at the histograms. Let me just pick this, for example. I don't want to go much into it. It's just an introduction to show you what to do and where to find what to do. So you can do histogram, say continue, and you do OK. So you find the statistics here, current age and height, valid, no missing, right? And valid 100, so you have 100 cases, mean, median, mode, all the things you want here, minimum and maximum for age, and same for 1127 for height. Now you find, oh, okay, if you don't want frequency table, sorry, it's clicked, it's checked somewhere. If you don't want it, if you want to use frequency for continuous charts, so you checked here, you remove it from here, and that's fine. So I'm rerunning. Okay, so without frequency, so this is your descriptive statistics, and this is your histogram. So you're seeing age, you can see not normally distributed. If you understand the bell shape that we I showed you before, you can look at this. This is terrible. No, it's not. So of course, whatever you're going to do, if you have this kind of distribution, you opt for non-parametric test. However, this is just dummy. I just produced something, so it's not following any kind of natural order or representing any reality. It's not. It's just to show you what you can do. But ordinarily, it should, if it's good data you collected from somewhere that's trying to represent the reality, it's that tendency that you should have that the bell shape, also depending on the number of your sample size or number of observations you have. Okay, that's fine. Let me actually delete all this so to create space for other tests. So that's how. So your description, then you also go back to, you can go back to analyze. If you want to run, so here you also have you can also do your descriptives for continuous variable. So you have current age here, go to options and tick all that is applicable that you want to do. And once you're done, continue. Okay, like you have, okay, some, so you can have it in this form. Okay, you can do more than that. Maybe having more heights, met scores, all the scores. Okay, so all in this, oh, sorry. I'll pick only this. So you have all the continuous variable in scale type, have them all and descriptives, and this is how it comes out. So sometimes the table looks, good and clean and very easy to read. So you can decide on that. Then if you want to run your categories, you go to descriptive statistics, you go to frequencies, that's where you run your percentages and proportions. You don't need this for that is only categorical variables. You can, social status, ethnicity. You have your control down and select whatever you want to do. That's how. So something like that. Marital status. So put them all at once. You can uncheck all this because you're looking at and check all of them. You're interested in just frequency. So you can look at charts. If you want to buy a chart or pie charts for frequencies, anyone you want, you make choice here. Frequencies and percentages. If you want percentages, fine. If you want it in frequencies, you choose here and leave all that. You can choose any order you want. Okay. These ones, leave them at default as they are. So here, then yeah. So you have your display your frequency tables. Okay. So you have to check that. Once that is done, so you can find all ethnicity, different frequency, percent, valid, and so on. So you have everything the way they should be. No. Okay. I've told you about this, that you can record them as you want. So this is just that. And I would also want to tell you more something about, there are situations, you can find it here, where you can find valid. So what valid percentage, you can find percent and valid percentage. So valid percent. So percent considers every data, including missing, all data, not all data, all the cases, including cases with no data. They're all calculated as the percent, right? Valid percent means all cases that have valid data. So it's excluding missing cases. So in some cases you'll find small difference. So difference between these two, you find in your chart is your own chart is just to know that this considers the missing into it, why this doesn't consider missing data. So all the cases with missing data are excluded. So you have only valid percent, and this is what you should report, in your research, and that's what you should consider. Missing doesn't have any data, so we don't need to put that. That's for descriptive. Quickly, so let's run through inferential statistics. Okay. So t-tests analyze. You go to compare means. So under compare means, you find whole lots of things that you would want to do. You have the one sample t-test, you have the independent sample t-test, paired sample t-test, like I mentioned, where you have a related one group with related measures taken from them, pre and post. This is where you find the pre and post test if you want to run that one way and over. So you find everything that has to do with comparison, like you find in that last category I showed you in the chart. That's where you find them all boxed in here. So you don't need to go too far. So you can pick one sample t-test, for example. So let's consider one sample t-test. Let's consider scores, for example. Let me say total scores. Okay. So you want to test the mean. You want to compare the mean of this group of people, their total scores, with probably reported total scores in the school in the past. Maybe the past graduated students or class of students from the school had their mean scores was 78. So it's reported, it's published or something. So you just put the score test value here. Then where you have yours, so just to compare what you have here and what you have here, that's all. So I think leave this as it is. Okay, and that's very simple. So you find, so the one sample t-test, you have the statistics here showing the standard deviation, the mean, the number, it's a number of cases here, 100, okay, and standard error. So here you are comparing this with test value is 78, and looking at this comparison, what is it showing? It shows that the difference between the mean score of your study sample of students with the published or theoretical one, as the 78, is highly, very, very significant. Okay, statistically significant. And this is where you read the p-value, the SIG, two-tailed. So this is very, that means is, of course, we set our p-value at 5%, 0.05. Okay, so if it's less than 0.05, that means the p-value is very, sorry, statistically significant. But if it's greater than 0.05, that means there's no statistical difference between the two groups. That's what it's saying. But here, it's saying that the difference is quite, so probably your group having mean of 106, performed a lot better than the past. So that's this. So let's go back to another test. Go back to compare means, like I told you. Then you look at independent t-test. So independent t-test, where you have you're comparing two groups that are exclusively mutually exclusive. They don't have any relationship of any sort. So we could also look at the same score, total score, put them in test variable. That's like our outcome variable. Then the groups you want to consider, you look, like I said, two groups, just two groups. So you can look at sex, so you have male and female. You want to compare the scores of male and female, in the same population. So here you have to define the groups when you have these two arrows. I'm sorry, these question marks. So you have to define the two as group one, depending on how you just, I think it's, you need to check how you code. Sorry, let me go back. That's what you need to check. Okay, cancel. Let me go back to, so sex, okay, 2, 1. So let's assume, okay, 2 male, 1 female. So you just need to be clear on that. So you go back to compare means, go back to independent t-test. So here we are looking at total scores between male and female. So you can define it. So group 1 is 1, group 2 is 2. That's what you have. In case you could have 0 and 1, so you put 0 and 1 if you have the codings, and you say continue and okay. So what do we have here? So here you have your descriptive statistics here, the number of, so you always have 1 and 2 because it's not coded in the SPSS like I told you. So if you had coded it, so you could find male and female depending on how you code them, which one is 1, which one is 2. So here, let's assume the first is female. So you have 36 number and the males are 28 and just normal statistics. But this is where you want to make some, read your results and report. So things that you consider here is this F value is important. It's called the Levene's test for equality of variances. So it's under the assumption that the groups, you pick them from one population. So they are not, there's not, far, you don't want them to be very different, vary in many characteristics. So you're looking at just one group. So they have, you want to see that the variances in in that group is about the same. There's no very statistical significant differences. So in this case, you want to make sure that the SIG as the p-value is above, greater than 0.05. If it's less than 0.05, then that's not what you want. However, you have an option of reading from the second row, which says equal variance is not assumed, but we wish to, this is what we want to see, that there are equal variances. So you're expecting that the p-value should be greater than 0.05. Then if that is done, then if that is what you have here, then you read here. But if this is less, like I said, if it's less than 0.05, you read from the second row. Then what you're looking at for is this, the t value is 0.3, very little, very small, and you can see the p-value here is far greater than 0.05. So what is it saying? That there is no difference, even when you look at the mean values here. For female is 113, for male is 111. So it's saying that the differences are not statistically significant. So that's why it's less than, it's greater than 0.05. But if it's less than 0.05, that means there's no statistically significant difference between the male and female scores. and that's what you would want to report. Okay. Okay, so let's look at the next one. Analysis, compare means. Okay, let's look at paired t-tests. So in this case, like we mentioned, you have post pre measures and post measures, pre-intervention or post-intervention, depending. You can, construct it or read it in design in any way, but just to make sure that it's the same group and you're taking two measures from same group, pre and post. So I have scores here. So this is the pre score, variable 1, and the post score, you put it in 2. So this is just the first pair. That's looking at one sample, and it's just as simple as that. You don't want nothing here, and you would make sure that you have 95 confidence interval. That's okay, and you go on. So what's saying? So the results say here paired sample statistics. As define statistics like as usual, the paired samples correlation. So here you want to see how the two samples, correlate, and that's what you find here. So number of cases on 100, while the correlation here is minus 0.1. Minus 0.1. I think they are not correlated in any way. Looking at that, something. Correlation is when you're having something very close to 1. 1 is the perfect correlation, when it's perfectly correlated. But if it's, heading towards 0, like 0.1, 0.2, or 0. Whatever, like have here, minus 0.1, which is on the negative signs, means that shows the direction, like they're kind of inversely correlated. Maybe when one is going up, the other one is kind of going down, but two of them are not moving in the same direction, so they're inversely correlated. That's why you have negative, and that's what it says here. Then for the paired sample t-test, so the reading, of course, I could tell much from here. Already you can see the t-test is 10. Like I said, the negative just shows you have the mean, standard deviation, and everything, but you are looking at the t-test, which is 10, quite reasonable, and it's saying that is statistically significant, at less than 0.01, 0.0001. So when you see, let me just say that once you see anything like this, p-value or sig values at 0.000, it doesn't mean all zero. It means it's very, very, very little. It's very, very little. What it means that the chances of getting these results, the probability of getting this result by chance is very, very minimal. It's less than, it's less than 0.05. So, but this could be less than 0.00001. It doesn't mean zero. There's still value, just that it shortened it at 3 decimal places. So that's all you could interpret here, if that's what you're running. So you're saying that the pre-values, the intervention might have worked, depending on how you want it to work. Do you want it to reduce the values? Probably what you got in the pre-measures. You've given an intervention that will reduce certain rates of temperature, workout rate or whatever. So after the post measures had shown that it has, drastically reduced, and you will find it here. And the pretest says, okay, sorry, the other way around actually. So the pretest says 28. So you're providing intervention probably to help increase the scores, whether the scores or whatever, depending on whatever you design, but you just want to see the measures to increase. And that's what you're saying here, that yes, there's huge difference between the two, after the intervention. So that is fine. But like I said, it's a lot of design. I'm just trying to tell you what to do. When you're running your own study design, you know what the implications of your studies, the aims and purposes, and how you put them into perspective and context. Your interpretations. So let's go to the next. So let me kind of clear this to have clean space. So compare means, in the last one is one way and over. One way and over. So like I explained, one way and over means just looking at one variable with more than 2 categories or levels. Okay, more than 2 levels. So here, let's look at scores, maybe math physics scores as the dependent variable, that's the outcome variable, and you want to see if these scores compare, how it compares across What do I choose here? Marital state. Okay, let me see. I don't know. Educational level. Okay, we don't have it here. Okay, yeah, it's not here. You might not have it here because, like I told you, SPSS reads in strings. So probably educational level in that Excel summit, even you can have them in numbers, but if they are in strings, then it wouldn't. That's the problem. It's good this happens here. So let's go back again and check and tell you something and show you what I want to see. So if you look at the data set, you have, go to variable view. I see educational string, right? So you have them in string, probably they're all in text. So we need to convert code them, put them in numbers and recode them in SPSS for it to read. So it shouldn't be recognized when you're doing inferential statistics. That's just one of the problems I mentioned to you earlier. So if it's in strings, you wouldn't use it. But let's go back and see anyone that the system provides for us to use one way and over. So like I said, we are looking at physics scores. So marital status, yeah, or social status, for example, yeah, because you can see two means I've already, recorded them in numerical values. Okay, so you have it here. So for one way and over, I don't think you have much to do. You leave this as it is. Post talk. Okay, you might want to, let me say 2K. For some reasons, if it comes out, I'll show you why I'm picking it. Everything could be the same. Okay. Options, homogeneity or variances, like I told you, you need to be run through this assumption to say that yes, they are homogeneous. Then continue and everything, you can leave it as a base. Then okay, click OK. Oh, okay, so what you have here, so test of homogeneity or variance, like I said, you want to be sure that the significant level is greater than 0.05 to show that there is no, it has, it meets the assumption, the conditions of homogeneity or variance across the three levels. So to say they are coming from the same group, there is no difference, bias difference or any predetermined difference. So it's from the same population. That's fine. Now you go to this here, ANOVA. And ANOVA, what does it say here? This is the main table that you would want to report. The F value is 0.2, which is very little, so I expect any significance. So what it's saying is that looking at the physics scores across the social status of the class members of the students, that there is no significant difference across. So one could say that the social status suggests that the social status might not have any significant effect in the scores of the students, physics scores of the students. It doesn't, might not affect them much. So that's what it says. Then the post hoc text, that's why I picked the 2K. So ideally, if you have any significance here, we want to check here to see which of the pairs shows the significance. If any pair, maybe between the middle and the poorest, or the poorest and the rich, if any pairs shows any significance, it will report here. That's what you will see. So rather than just reporting, yes, that is statistical significant difference across or between the groups or levels of the social status, social class, you would want to see exactly which of these levels. So that's what 2K is called, multiple comparisons. That's post hoc test, multiple comparisons. So that's what 2K will do for you. So if there is any, you find them here, then the significance level would be less than 0.05. But I'm not expecting anything to be less than 0.05 here because generally there is no, in the general ANOVA value results, there is no statistical significant difference here. So the p-value is, still greater than 0.05. But if it's less, you definitely find at least one of those pairs shown. So you might want to report that as well. It's something we want to see in your report if that happens. So that's here for you for ANOVA. Okay, I think I'm done with comparison of means. Okay, so this is fine. So we check the next one, which is contingency. Yeah, contingency table. That's where you find your chi-square. So where you got that from descriptive statistics and crosstabs. You want to see crosstabs, you want to look at, and like I said, in chi-square, you're looking at two categorical variables. You want to see how this variable is associated with this variable. So let's see what we have there and see what two categories we can combine. And from the crosstab here, you can choose chi-square as one of the statistics that you want to run. Okay, so here, what do we choose as row? You have the rows and you have the columns. So usually you would like to find the outcome variable on the columns, the perceived suggested outcome variables in the columns, while the other will be the rows. So let me look at what could I use to do that? And it has to be, okay, no, not necessarily. Sorry, I don't have anything in mind. Evidence of vaccination. I don't know. Okay, maybe I will have to check. Do I have something on COVID here? Evidence of vaccination. Okay, sorry, before you do that, sometimes just check the view, so just to be sure what you have. Okay. So you have educational level. No, I just want something related to ever childhood immunization. Okay, let me look at this, and it's so I would like to always want to use strings, like the ones that are in numeric. That's just for you to, like I said, you have good variables here, but the strings you have to be converted in numerics. But because of time, I wouldn't want to. Okay, I don't have any that I could use. Just do illustration. I don't have something before. Okay, let's just do this. Let's check social status and see if social status is associated with educational. No, this is still. Okay, just for illustration. Okay, let's say just marital status. I just want to education status and marital status. Okay, so you go back to analyze, descriptive statistics, crosstab. So you can have any, let me say, social status as rows, and marital status as columns. Just something for illustration. But here you might want to have something like maybe something like, for example, like you want to know how many people who have taken COVID vaccine, among the students or among whatever population you're working with. So you could have taking vaccine as the variable, or COVID vaccine, yes or no. That's the category. So you want to have that in columns, and the other social, I want to see if social status or educational level, whatever, could be associated with or have any kind of effect on the probability of taking COVID-19 vaccine, as in yes or no. So that's how you have such kind of relationship. So, but just for illustration, so you will have this here, and you go back to, so this is where you check, the option of chi-square or chi-square. That's the only thing I think you might just want to, and that's fine. Leave this as it is. Cells. Okay, under cells, you might want to look at your row percentages. Yeah, you want to see row percentages, total if you want. These are options. Continue. Then you don't need anything here, nothing here, and leave the rest as it is. Then, okay, you want to display clustered bar charts, fine, you can do that, but I don't think it's necessary. Okay, so you say okay, and you have your cross tabulations. So you can see your marital status because it's not been coded. So you can just find 1, 2, 3, 4, but that could be single, not married, single, separated, married, or whatever. That's what you find here. So what you want to see here is you want to see what are the observed. You want to look at the social status against marital status. So what percentage of this group who are poorest and not married, for example, or group 1 of marital status, what percentage are they, and what percentage are not married and poorest and group 2 of marital status? Then the same poorest and group 3, maybe singles, and that of the last group. So you just want to look at the percentages and the absolute numbers. You can see 3, 1, 1, 1. This is not good. You know, this is not good. Usually, chi-square correlation tables might have chi-square in particular. Sorry, you might see I call it they have different pronunciations. They call it chi-square or chi-square. Anyway, so you have this another assumption condition here that each cell would have to be greater than 5. So cases where you have some cells less than 5 here, and that's a problem. So it's just a question of numbers, but I have only 100 cases here just for illustration. So in your report or result, definitely you have a lot more than that, you know, and you should be able to have, in some cases when you have too many levels like this, have too many levels, 4 levels of marital status and 4 levels of social status, you might just want to reduce them to 3 levels or 2 levels so that you'll be able to have cells, you know, just compact numbers and you have cells that are 5 or more. That's another way of correcting such situations. Okay, so but here just to find what you can find. So these are the contingency table. You see how it relates. So you can see if certain groups are more compared to others across the marital status or across the social status, you know, and it's just clear descriptive, something you can read and make an interpretation. Now, when you go to chi-square, okay, you can look at this assumption here. 9 cells, that's 56.3% of the cells have expected count less than 5. The minimum expected count is 0.64, right? So what it's saying is it's less than 5. Like I said, it should be 5 and above. It's one of the assumptions. So once you find this kind of situations here, then you be very careful in your interpretation of that result. That's what it's saying, that the results might not be very, very valid because it doesn't meet the assumptions, and so could be biased in some way, or could have some erroneous computations that might lead to erroneous interpretations. That's what it's saying. So, however, once you find this, assuming that all things, you know, being right, you look at the chi-square. So what you find here, this is what you read, the Pearson chi-square, and check if it's significant, statistically significant, which is not. It's, you know, greater than 0.05, and the value here is just 14, which is very, very little. So you wouldn't expect much from there. And when you want to report, what you report is this value and probably the level of degree of freedom. I didn't say that in ANOVA and in the past test, you know, but what you should, degree of freedom is also very important. It gives us an idea of the levels of the variables and, you know, chances or degrees of variability that one could find in the results, considering the levels of those variables that you used in the computation and the analysis. So it just gives us an idea of that. So it's also important. So you can report, say something like chi-square in brackets, degree of freedom, comma, then the chi-square value, comma, and p-value, comma, or like that. Or you can say a chi-square in bracket degree of freedom is equal to this value, you know, comma, comma, and p-value, you know, maybe less than or greater than 0.05. That's what you do. Okay, so that's fine with this. Then, like I said, it's just an intro. Though I'm doing quite a lot more than intro. What I think that if you follow this carefully, diligently, you'll be able to run your own statistics, you know, or with less support from anybody. It's more than intro, but there are whole lots of things to talk about, whole lots in SPSS, but just the ones I think that will be very relevant for you. Now, next should be, I think, yeah, the regressions, the multiple logistic regressions and the linear. So for the linear, you go to regression from analyze regression. From regression, you go to linear. You click linear. And here, like we explained in the decision tree for your statistical test, you should be able to have multiple independent variables on continuous data type. They're all continuous data type with a continuous dependent variable. Okay, so you want to check how these are, how they could predict the outcome variable, how they, how well they are related, associated with the outcome variable. So in that case, let's say, okay, let's say for example, total score. No, okay, let me just say, okay, total score, right? Let's use that as the outcome variable. Let's see how physics could predict. You have it in independent dependent variables. So you have physics. What else again you can have? You could look at, just for the illustration, current age, height, any other thing. Just let's look at these three. How it predicts. It has to be more than two, independent variables here for you to use this. Then you go to statistics. You can choose R square. You want to look at the descriptives, fine. You want to look at the collinearity diagnostics. This is fine. It's also one of the checks, tests of assumptions of multicollinearity. You don't expect all the different the dependent variables to relate to each other. We don't want that. So we assume that they are not related to each other. So this is one of the diagnostics that we use to check that if you pass that assumption. Okay, fine. Oh, confidence interval, yeah, you need to check that 95. Then that's fine. Plots, you might well, just leave this for now. Do you want anything here? Okay, you can leave it as it is for now. Nothing so, okay. Options, that's fine. Leave it as it is. Style, leave it as it is. Okay, nothing about bootstrap here. So that's fine. And as simple as that, you can just say, okay, let's see what we have here. So here you have statistics descriptions, like you want to see the mean, standard deviations, number, all cases 100, no missing values. Then look at the correlations to see how each different different variables, how they correlate with each other. So this is Pearson correlation. You want to look at this score total will definitely relate perfectly well. Like I said, 1 is a perfect correlation. So you would expect that they have perfect correlation with each other. So score total with this should be 1. With the physics score, you can see this is 0.02 with current age 0.1 and with height 0.07. So these are different correlations if you want to see what it looks like. But this, your concern should be just model here. This is first what you want to look at. And what are you looking at here? You want to look at the R square. The R square or adjusted R squared, which is very close. This means just kind of the adjusted, the standardized, R square. But what is trying to say? You have 0.82 here, which is very, very high, very, very high. What it says here is that you want to know how much variation in the outcome variable can be attributed, accounted for by the independent variables. So the changes you find, the variations you find in the outcome variables, how much of it can you attribute to the changes in the independent variables, the age, the height, the physics score, right? So that's what it's saying. So, and you interpret this in percentage, just multiply by 100. So you can say that 82% or the variations or variances in the outcome variable, that's the high score, the total score, could be accounted for by the independent variables, the height, the physics scores, and the current age. That's what it's saying. So we just want to see how much more of influence that this could have there, right? So next is the coefficients. This is where you now want to read the main score. So when you look at here, your interest will be in the standardized coefficients beta. This is unstandardized ones, but you just look at the standardized coefficients. So you can see physics score is 12.6 and current age 12.4. Very, very similar, but on the inverse direction, the opposite direction, and height is 0.024. Okay, and now what it's trying to say at physics, it's of course it's very, very high. Like I said, it's a dummy data. Probably I must have duplicated physics score as age and made some adjustments there. So that's why you're seeing it this way. But just for illustrations, like I said, okay, so it's showing that physics is very, very highly significant. Of course, it should be, because of course you know that physics is also part of the constituents of the total score. We added it to get the total score, so it's a clear expectation. Well, I deliberately used it so I could to show you what it looks like. So I'm expecting this, and the current age is saying that okay, that someone's age could influence the total score. Your performance in your exams. So your age could perform that, but it's like on the opposite. When you see a minus, it's like the opposite. The older you get, the poorer your performance. While the younger, the better. That's what it's just saying. So, but it's highly significant as well. So in your report, you report this coefficient and significant level. Yes, you can do that. Or what's it called, the confidence interval, confidence range, the lower bound and upper bound. You can report that just to show why you discover that height is not significant. Of course, the standard coefficient beta is very, very low, and the t value is also low, and you can see it's it's greater than 0.05. So that's not so when you report, so you say that these are the two factors that are making more contributions or influence more associated, statistically significant associations, demonstrating that with the high score. That's how you report there. And again, you can also make this report single report by saying these are the changes in the level of change in the outcome variable by just a unit change in the independent variable. So for example, what it's saying here is that a unit increase in physics score could lead to additional 12.6 units of total high score. That's the interpretation. Why this is saying additional increase in age could lead to reduction in the total high score by 12.4 units. Now, okay, this is where the collinearity diagnostics. Here, you just focus on the Eugen value. Eugen value here, you don't want to have too many zeros here. You don't want to have too many zeros. Okay, so if you find too many zeros, like though you have only 4 categories, levels of checks, that's dimensions, 1, 2, 3, 4. Like this is showing that there is possibility of collinearity here. But what you try to avoid, no matter, just don't, you want to see like this is good, this is good, this is close to 0, but still better than zeros. So that is it for the diagnostics. Okay, so that is fine. So let's go to the last analysis. Sorry, I know I've taken too much time this video. The last analysis, it's on logistics, binary logistics. So you get to regression and go to binary logistics from Analyze. Like I said, all analysis is conducted. You find them under Analyze. So you go to binary logistics and you click. Here, like I mentioned in discussing the the choice, the statistical choice, decision tree, you are looking at binary outcome variable, binary dependent variable. So which means it should have only two levels, 1 and 2. That's all. You could have two levels, and then you have so many other independent variables. You could have a mixture of continuous variables and categorical variables. You could have them, but what defines this test is that it has to be binary outcome and yes or no, just two possible levels, yes or no, 1 or 2, thereabout. So in this case, I don't know if I have that. I thought so I could have, except if I go back to so I don't have that. That would make meaning. I have sex actually. I could use that, but I thought I have something on number of. Okay, just hold on a second. Let me just look at this. If I could do a quick conversion. So I should have done that before now. Look at the data view. Okay, let me just run through. Let me just create one quickly. So here, let me just say COVID-19 vaccination, numeric. Okay, so you go to data view, the extreme. So all missing. So let's just do some entries here. Like, so let's say 1 represents, okay, 0 represents no, 1 say yes. So you have like, oh, sorry. It's good to just see how this is done. 1, 1, 0, 1. So this is how you have your entries. You might not have all this done now. Okay, so I'm assuming I'm entering 4 different cases. So for the, sorry, so you don't need to have, okay, so you could have some missing cases, let's assume, no? And in an ideal data set, definitely you have. Okay, so let's say this is what we have. Okay, we're on with it. Now I take you back to, okay, take you back to like the coding, like we said. So let's say 0, it says no vaccination, and 1 is yes vaccination. Okay, so this is fine. So we can run a quick frequency table on that reset just to see. Oh, okay, it's still in code. When you see it's still in scale type, so let's go back, change it to nominal. Yeah, okay, let's go back again. It shouldn't affect it anyway, but it helps SPSS to have good idea of what it's doing. So okay, so this is what we have here. So no vaccines is 46%, valid is 53, yes is 45%, right? So you have 10. That means, do you see what I'm saying? This kind of thing. So now here, the percent considers both this and missing values. You see, my system missing values, the ones I didn't enter. So it considers all as part of the percentage and it's giving you 100. So, but in this case, you want to remove missing data and consider only valid data. But again, you have 10. It's a good example of the kind of error you could have in data entry. And how do you dismiss it? So you want to make it missing so that you are telling SPSS consider 10 as missing variable. Okay, so let's go back and see. You go back to we go back to data view, missing. So you go here, you say you're instructed to consider 10 as missing. Simple as that. So you can run this again and see the difference. So you can see 10 becomes missing, included in the, part of the, you have added to the system missing. So this is the valid now. So here you have 54% of the population have not had a COVID vaccine, while 45% have had COVID vaccine. So we can work with this for, that's a good one. So, sorry, regression, binary. Okay, good. So binary logistics. So thank you. Take it to dependent variable. That's a good one here. Quickly created to make sense. So you want to look at social status, marital status, how they could, what else again? Okay, let me use, and age or height, just for illustration. No, these three, to see how they could predict the possibility or probability of someone having a COVID vaccine, and is it related, with, could it be associated with your height? Okay, let me use age. That's the one that makes more sense to you. Could it be associated with age or marital status or social status, or could all these predict the possibilities of having COVID-19 vaccine? That's how you can have that kind of research questions or design your hypothesis there to say there is an association or there is no association. The null hypothesis says no association. Research hypothesis or alternate hypothesis says yeah, there is an association. Okay, between this and that. So you have them entered. Then you check the categories. Yeah. So you need to tell SPSS which of these are categorical variables. So social status is one, marital is one, current age is not a categorical variable. And here you are saying here that that system can use the last category of these variables as the reference category, as the one that you use to compare with others. That's what's called the reference category. You can decide to use the first variable, the first category or last category, anyone you want is fine. Okay, you say change, continue. Here, would you need to do anything? No, it's fine. Options, yeah, click confidence interval for exponential B. Exponential B is the odds ratio with the confidence interval of 95. That's fine here, continue. Style, nothing. Bootstrap, nothing. Okay, I think we're good to go. There are more methods. Yeah, you can just leave it at default, enter, but there are reasons why you may want to use any of these. It's something like you want to read up, but for now, data is fine, and enter is fine as the method of entry. Then that's okay. So when you do okay, what do we have here? So I'll just take you straight to what you should want to focus on, right? Yeah, there are so many things to read. So here, you go straight to, you have the case processing summary, if you want to look at that. You have the encodings, like you have 0 and 1, yes or no, internals for the dependent variable. So you want to look at that. You want to look at the categorical variable codings. What it's trying to say is, like, for example, marital status 1, you have 1, 2, 3 here. So it's coded as 1, 1 is coded as 1, 2 is coded as 2 here in the analysis, 3 is coded as 3, while 4 is the reference category, so you won't find any coding because you use the last level as a reference category. So social status here, how the poorest is coded as 1. So this is what you will see in the table where I will show you, where you pick your results. So it just when you see 1, you know that is poorest, poor is 2 here coding, and 3 is middle, then rich being the last as the reference category. That's what you use to compare with others. Okay, so you jump the beginning block 0 here is just saying what the model looks like when there is no equation, when there is no variable added in the model. So you can see variables not in the equation. So no model is in the equation. This is what it looks like. That's what you want to see, but that's not your interest. Your interest is on block 1 when you've entered some your variables. So what would you see? Okay, your interest, like I said, you just focus on looking at the R square, like I described earlier. So you can see here, so R squared, you find Cox and Snell, and I don't know how you would want to, but I usually call it Nagel or Nagel Keke, but just Nagel's R square. If you want to, that's fine for you. So this is the R square, like I said, this is where you interpret the level, the extent of influence that the independent variables have on the dependent variable, you know. So you want to say what percentage or what proportion or what percentage of the variances could be attributed to the independent variables. So that's what you see here. So Cox and Snell is 12%. They are always very, very related, but Cox and Snell is always a bit more conservative than Nagel-Kekel R square, but you can use anyone, preferably sometimes I go with this, but just mention the one you're using, that's fine. Okay, then you also want to look at this is the main table you will report. This is where your main results is. So we want to see in your results the R square of the model, R square value in percentage. This is 12.4, 16.5%. Give us an idea of the extent of variances could be attributed. Then here you focus on, yes, for logistics, binary logistics, this time you might want to focus on the odds ratio. This exponential B is the odds ratio. That's the odds ratio. And what would you find here? So like I said, if it's social status 1, 2, 3, I've showed you how to read the coding, which one is 1, 2, 3. That's what you find here. You don't just get the variable names or codings here, okay? You also want to find here. So here, for example, exponential value here is 0.196 is on the negative, 0.196. So you can find it on the negative. You might find on the positive. Here, marital status here is on the positive, 1.7, and here on the, so all you just need to do, and but by looking at this, you could know which of these is statistically significant quickly. For those who do not know how to interpret confidence interval, when you look at the statistical significance of the word child square value, you can look at the significant values here. You can see all of them are greater than 0.05. That is to say that none of the variables, independent variables, is statistically associated with what vaccination, COVID vaccination. None of them could be used to predict confidently the outcomes of someone's taking COVID-19, a vaccine. That's what it's trying to say. None of them. And because of that, we don't need to just say that's just the result, none. But assuming that you have any significance, for example, maybe you have something like 2, 3.0 or 3.196 here, then and definitely this will be significant if you have such scores, and you also have statistically significant confidence interval. You can also have that here, right? So usually if you have that kind of such, so one will say that, so you're comparing social status 1, if I remember what that is, poorest, right? Comparing poorest to the least was the highest, rich. So comparing poorest to rich. So you're saying I'm just giving it as an illustration. It's not a real, like I said, it's not a real life results or expression of what's in the reality. So that's not that, just for expression, for illustration, like I said. So what you have here, so you have something like 3.0. So you're saying that the possibility of having COVID-19, the chances or the odds of having COVID-19, or that the poor people have you have two ways you can represent that. You can say the chances or the odds of having COVID-19. We have 3 times higher odds of having COVID-19 than those of the rich people, having COVID-19 vaccines, sorry. So you have 3 times odds or chances of having COVID-19 vaccines than the rich people. I mean, that's for the poor, but that's how you can interpret that. You can also want to interpret in percentage, and what could say there is a 300% odds or chances of having COVID-19 vaccines among the poor than the rich. There are ways you can have that. Then you can also, if it runs on the 0, that means on the negative, if it's like 0 point something something, that's I wish I could have run a calculation here, but maybe so to show you how. So usually you just do 1 minus 0 point whatever you find, 1 minus 0 point whatever you find. What you get there, you convert it to percentage, and you can say that the poor has something, let me say 70%, chances of not having COVID-19, because it's now in the reverse case, the inverse value. So 70% of not having COVID-19 than the rich, or 70% odds of not having COVID-19 vaccines than the rich people. So that's the population. That's how it's interpreted. And then you show the odds ratio value and the COVID-19, confidence interval, associated confidence interval values there. And if what I also wanted to look at again, is a bit technical, but you also want to find out that if this p-value is statistically significant, or any confidence interval that is statistically significant, it won't have, anytime you have any confidence range, as in lower and upper, crossing over 0 to 1, crossing over 0 or crossing over 1, so from 0 to 1 point something or 2 point anything or whatever, that means it's not statistically significant. But if you have the range all in 0 range, 0 point something, that is less than 1 or greater than 1, so you could have 1 point something to 3 point something, 2 point something to 4 point something, whatever the range, 4 point something to 16 point something, whatever the range is, that is statistically significant. That's how you know confidence intervals that are statistically significant. So because they are either the two upper and lower values or range is either above 1 or less than 1. It has to be either of these two sections or parts. It doesn't have to cross over. If it crosses over 1, that means it's not statistically significant. So that's how you could know that. So far so good. I think I've taken chunks of time, a whole lot of time. I might end up making this video part 1 or part 2 in case if you find it that way, for it to be easy for you to run through. But I just try to make the best use of what I think that to be very relevant for you. You can confidently run your analysis, your SPSS, by yourself, or at least have certain level of confidence in doing the analysis yourself. And this is what it is. And here we come to the end of this introduction to use of SPSS. It's quite a lot, but I think I've given you more than enough of introduction that you can work with. So at this point, I would say best wishes. I wish you the best of luck. Probably you might have time to have more discussions on this. Okay, bye.